Hubhopper Originals.
To start your podcast for free, log on to studio.hubhopper.com.
Hello everyone and welcome back to Indian Genes. Once again, a big thank you for the response we have been receiving to all the earlier episodes, and we are happy to say that our new and well-designed website is now up and running, so we would like to encourage you to get there. It's at www.indiangenes.com. A big thank you to Hafiz Abu Bakr for assisting us with this. So do have a look and subscribe, comment. We look forward to listening from you. We have a very interesting guest today who is leading an initiative to establish India's first center that will work towards studying the origins and distribution of life in the universe. Prior to this, he has experience in building sample collection instruments for Mars and Venus surface missions while working with NASA. He received the NASA Spaceflight Awareness Team Award and the NASA Ames Technology Transfer Award for 2 successful spaceflight experiments on board the International Space Station and co-owns a registered NASA planet. He has led international expeditions to explore extreme environments in Ladakh and currently is involved in something very interesting that he is setting up at Ladakh. I will let you listen to this particular discussion, and there's a lot here that you're going to really enjoy. There's a lot you're going to hear for the first time, and I'm sure when he did what he planned to do, making a big move from NASA and coming down to India, that was his goal, to set up an exploration center for space and for environments in Ladakh itself. He decided some time ago to move back to India to set up a space exploration program at a particular location, which is now Ladakh. And this is going to serve a lot of students and space enthusiasts that want to understand a little bit more about the environment, not only here on Earth, but on exoplanets, including Mars as well. So to all our listeners, this is an extremely exciting episode. And Indian Genes is now proud to bring you none other than Dr. Siddharth Pandey. So hi Siddharth, and from everyone here at Indian Genes, a big welcome to you. It's an absolute honor and pleasure to have you spend your time with us here talking to us. So for all our listeners, Siddharth, why don't you tell us a little bit more about yourself and what you are actually up to these days?
Thanks a lot for having me, Joachim. It's quite an honor to add to the impressive list of speakers who have spoken at Indian Gene Podcast before me. So I am Siddharth. I'm at Amity University in Mumbai, heading a center for astrobiology, Center of Excellence in Astrobiology. And I have, like I was speaking to you before we started recording, I have been a Navy brat. I've grown up the son of a naval officer, lived around India in different regions, and did my undergraduate in aerospace engineering from Amity University itself, and then a research fellowship at IIT Bombay. And ever since, I've been jumping regions or continents for my education and work. So I moved to the Netherlands for my master's in space systems. And from there, I moved to NASA in California, where I was working on microgravity experiments, so experiments that are operated in low gravity environments, as well as Mars-specific hardware development. So those were the 2 main things I was working on while at NASA. From there, I moved to Australia, was able to get myself a PhD, and the work also related with Mars surface missions, where we were developing ways in which we can ensure that rovers do not freeze on Mars. So how do you keep a rover warm on those cold Mars winter nights? And also, while I was at it, I was able to work with teams that actually take Mars instruments to different places on Earth which are similar to Mars. So I'm talking cold, high altitude, dry desert environments, something similar to Ladakh or the Atacama Desert in South America or Antarctica. And these are perfect places for you to see how the surface has evolved, the geology of the place has evolved, what kind of microorganisms are living in such extreme harsh conditions. And as an engineer, my role transitioned from being a pure engineer to a research engineer. So someone who's not just involved in the engineering side of things, the technical side of things, but also helping develop the scientific scope of a particular project. So that kind of gave a different dimension to what I was doing, which was initially just doing a few calculations and trying to optimize a specific system. Now I was working with scientists and helping understand how well we can, come up with different kinds of ways in which we can capture whatever they need. So whether that be a sample collection system or a drill, or a specific instrument that needs to be designed in a certain way. So working closely with scientists. And that brought me back to India because I was offered this position to set up this new center for astrobiology, the first center in India. And I've been working since 2019 now, closely with our different partners in different capacities. So that's kind of a very long, short summary of everything that I've been doing for the last almost 15 years now.
Earlier in your life, you mentioned you had to move around as a Navy kid. That was not your choice, but now by choice, you seem to have inculcated that travel bug in you and you keep moving around.
Yeah, it's kind of, played an important role in my life. I've noticed after about 3 to 4 years, wherever I am, I start getting restless. And I really feel the need to move to a different geographical location and also take on a newer project. So it's kind of, been a feature, at least over the last 10 years since I moved out of home.
And for students listening to you at the moment, Siddharth, I just am trying to understand your trajectory as far as your career goes. When you started in aerospace engineering, is this the normal outcome that generally happens, that you would move in here, or were you moving according to what your interests were as they developed? Or did you have a plan in mind when you went into aerospace engineering 15 years ago that this is the route I'm going to take?
So it's not a conventional route to reach where I am currently. But I can say this, that a lot of people who take up aerospace engineering in their undergraduate, many of them who are interested in research do transition into space systems, because aerospace systems at an undergraduate level doesn't do a lot of space related stuff. A student who is doing aerospace, he is mainly concerned with atmospheric vehicles, so aircraft or helicopters, and maybe a little bit of rocketry. It's only in your masters when you get a chance to take up the real space stuff, where you're working on developing mission designs or understanding astrodynamics, or further understanding thermal rocket propulsion. So until there, I was kind of on a fairly popular path as far as aerospace engineers are concerned. But the place where I kind of completely got off the road was getting into the field of astrobiology. And astrobiology is a field that's a very vast discipline. It's majority scientists, people from different scientific disciplines. So you have biologists, you have chemists, you have physicists, you have geologists, and to some level you have engineers who actually are mainly civil or mechanical engineers, or sometimes you have software engineers who basically work on developing systems that are specifically for a specific planetary science mission. So in that sense, I think I was driven by my specific interest, because the more I contemplated about what I wanted to do, the you can say more directed my path became in terms of where it has led me today.
Right, because you've been involved in a lot of research, like you mentioned, thermal design and field experiments as far as testing is concerned, or whether it was the Mars analog that you were talking about. And maybe we can break some of this down as we go in. A little bit technical, but it would be interesting to know from you. When you talk about astrobiology, how would you give us a brief summary about that for somebody who wants to know?
So anything and everything pertaining to life on this planet as well as in the universe is astrobiology. One popular way of defining it is the study of the origin, evolution, distribution of life and the search of it, beyond Earth. So it's not just biology, it's not just astronomy. It's a bit of understanding how the planet has come to be, how the solar system has come to be, and it has a lot more to do with fields coming together rather than one specific core discipline that one has to really look into.
And when you talk about astrobiology, starting off from the Earth itself, those are the principles that we work around for life. When we talk about life on Earth, we pretty much got that mapped. But do we take those same principles, assuming that we're looking for life in another planet?
Yeah, so we actually do not have a lot of things mapped out, and that is unfortunately what makes it really hard to look for life. But it is the only form of life that we know. So it kind of constrains in what we're looking for, but there is no other way. And by itself, I think it's quite a lot of information to start out with. So, like you said, it's something we start with, but we're working at both ends. We don't have life completely figured out on Earth, so there's a lot of astrobiology work that relates with the origin of life, of trying to understand how exactly did life start on Earth. And while we are figuring that out, we have a lot of clues about earliest forms of life on our planet, and we try to understand in what kind of scenarios, what kind of conditions did that arise. And once we have a certain sense of that, we take that piece of information and then we start looking around our planet on other moons and other planets and try to find ways in which we can correlate and see that is it possible to find similar kinds of environments that might have existed, if not today, millions of years ago. And then based on that piece of information, we design and develop missions that are then eventually sent out to look for life. And this Mars 2020 mission is pretty much a testament to that. It's doing exactly that. It's a mature mission that has been developed after discoveries that have happened over the last 15 odd years that have come from the other initial Mars missions. And so that's basically what it is. You build on what you have discovered, and then it's an iterative process.
And what is your current understanding or thinking on how life actually originated on Earth? Because there is a lot in popular culture, I could say, I'm sure in science as well, where we do hear about one is life originating in the soup on Earth, the other one being panspermia, or it could have come in via space through a meteorite. How do you look at this, and would you want to clarify this for us?
Sure. So it's a question that is hotly debated in my community, and there's sides that people take. So it's a very opinionated question that is hard to answer, without having a certain stand to it. So there's a lot of research that has recently come out, like as recent as just the last few weeks, which is further solidifying one theory, which basically claims that life actually started in shallow pools of water on beaches or shorelines, but very much on land and not inside oceans, deep on the bottom of oceans where you have these hydrothermal vents, because that was the other strong theory, which was claiming that life actually started in the oceans and then moved out of the oceans onto land. So there's a lot of work, and I've been fortunate to in fact have worked with a couple of scientists who work in that area of trying to prove that life actually started in hot springs and around hot springs on land, such as the ones that we have seen in Western Australia. Some of the oldest evidence of life has been found around active hot spring systems. So life really needs a lot of energy to start with, and it needs some kind of a medium for that energy to translate into chemical, exchange of information back and forth. And it's estimated to have an order of you need about 1 trillion chemical reactions to happen in a certain sequence or in certain combination for life to eventually start. So it's not just out of chance, but it's almost out of a calculated scheme of events that take place that we understand, before which life can actually start. So, and there are favorable conditions and non-favorable conditions, and it's very complicated to completely break down how life starts. But we are kind of inching closer towards understanding or making sense of some of the oldest land records that we have of life. So yeah, it's still very much open. As far as panspermia goes, again, it's a theory that few astrobiologists subscribe to. But again, life could have in fact come from space. We just do not have enough evidence to claim it. We've seen a lot of meteorite samples that have been discovered that actually had organics, which are pretty much the building blocks, for proteins to form, and proteins are the building blocks for life eventually to form. So there's a lot of, you can say, raw material that has been discovered, but what eventually became life is something that is still yet to be, completely confirmed.
The spark, where did the spark come from? I guess
exactly.
that's so interesting, because you were mentioning that even if a meteorite does come in and has all the building blocks, the blocks need to come together, and the energy that needs to be pushed in or generated to get things going. That's very interesting. And I was reading some time ago about, as you started at the very beginning with, by the way, what you just told us is very interesting, that life may have originated on land and not the other way around, because that is what we've been grown up to think and we've thought all our lives. But that is interesting.
Yeah. Water, in fact, has been proven to have hampered. It's very hydrating because of so H2O. A hydrating environment turns out to be not very favorable for life to form. So you need constant access to air for it to have developed. So that's something that was recently, in fact, confirmed again from land records, oldest land records from Australia. There's also a study that has been done with some of the oldest, material that has been discovered in Greenland. So yeah, it's something that is going to change what is printed in textbooks.
And you mentioned conditions, with obviously there have to be the right conditions, or there has to be a perfect setting for life to have evolved. Another interesting part also is, even once it did, the rapid expansion at which it moved all over the planet is absolutely stunning, because it could have still originated here. And what are the chances of it being divided, and generally equally divided, all over the planet?
Exactly. So, back then we didn't have the same kind of continents. Land masses were pretty much coagulated or, integrated. But then again, there was a lot of wind movement, water movement, dust movement from one place to the other. So there are a lot of these weathering activities that tend to transport material from one place to the other. And even today, like I was watching, a show on Netflix, which in fact informed me about how the Sahara Desert is actually feeding the Amazon rainforest. And it was so ironical to think about a bare desert, almost dead environment is actually transporting nutrients across the Atlantic Ocean and feeding one of the richest, regions on our planet. But that's the kind of global scale of transportation that is taking place in different capacities. And the same has been happening, over millions, if not billions of years, where we tend to forget that everything is connected in some way or the other.
Yes, and if you say that, then what comes to my mind is the Jaya philosophy, or if you look at the whole planet as a living organism. A great example is what you just spoke about, the desert feeding the Amazon rainforest. And then probably your perspective of everything changes, because you don't look at blocks anymore. You look at the whole, and you understand that every time there is an effect on any one part of it, there is going to be a reaction somewhere.
Absolutely. I mean, one thing for sure, what you said is fascinating about how life propounded and spread. But also, you have to keep in mind that this is a process that occurred over millions of years. So this is timescales beyond our regular imagination, because we tend to think in centuries or millennia. but this is like thousands of millennia that are kind of coming together and making this happen. So it's a slow, torturous process, but over the time, it kind of has, it managed to spread all across the planet and then get destroyed and then come back again and then again get destroyed. As you know, there were several extinction events as well that took place.
Tell us a little bit more about this very interesting time, which was the Cambrian Explosion. And why is that so exciting for so many people?
But it's just the sense of the different things that kind of came together. How life, which was a certain way, it was quite uniform in a certain way, how it kind of diversified. I think that is something which really left a lot of people flabbergasted as to how could things have suddenly become so diverse and so distinct as it wasn't happening before. So that rapid sense of diversifying is what the Cambrian explosion is. And I mean, both whether you look at animals or you look at plants, everything kind of just started multiplying. So it's again something which is, we have to look at the land records, you have to look at the fossils. That's the only way we are able to know. You have to go back to the rocks, because those are the books, nature's books of the stories about what really happened. And that's where all the information lies, because you not only get a sense of the organisms and their fossils, but you also get a sense of the atmospheres, because on many occasions you have gas bubbles that are actually trapped inside these rocks. And people have been able to analyze the gas bubbles or the size of bubbles also over time, that actually tell you about the constitution of the atmosphere at that point of time, and how that might have changed, and how even a few millimeters of layers below or above is actually going back, flipping almost 100 years to 1,000 years, in the future or in the back, in the past, in that duration. So there's a lot of information that we need to further understand as far as Cambrian explosion, and all of that is kind of sealed into a very narrow band of time that needs to be further understood. So again, it's an example of how we do not completely understand how life propagates.
And the interesting fact mentioned here, where you were talking about air bubbles or the early structure of the earth and what was happening geologically all over the place, in my mind connects with something that you spoke at the beginning of this discussion, and you were talking about the Mars analogue. And if we are going to go out there and look for other planets, then we need to first try to understand what we have right here at the moment, because it's as exciting, if not more.
Yeah, absolutely. And so we are we've just announced something called the Earth and Space Exploration Program. That will be a education research program that will be run in Ladakh from the 1st of June until the end of October. That will give a chance to students, space enthusiasts, faculties, researchers to be led by instructors. So we are arranging a team of resident scientists, and it'll involve a visit to Ladakh, a 7-day visit to Ladakh, and there will be a particular transect on which they will be taken, and there will be 3 different themes along which they will be trained. One is the past, so understanding the formation of a planet, formation of Ladakh. So Ladakh, not many people know this, but actually sits somewhere in the middle, where the Indian continent, once it was it detached itself from Africa, and then it was moving upwards and rammed into Asia, and that's actually what caused the Himalayas to form. And the Indian continent is slowly and steadily moving underneath the Asian continent, and you can see how the Himalayas are rising up every year. So talking about how plate tectonics plays a strong role in terms of how a planet is formed, and how plate tectonics actually affects how atmospheres evolve, how life evolves. So we'll be talking a bit about that, because in Ladakh, you can actually see very dramatic features of these plate tectonics. You can see almost near vertical layerings and all of these very dramatic geological features. And there was an ocean, the Tethys Sea, that was actually uplifted. And you have a lot of marine fossils and shells in Ladakh. So who would imagine that in a place like Ladakh, a cold, dry desert, you can actually find areas where there are small little shells of marine animals that were once living in this ancient sea called the Tethys Sea. So we talk about that. That is the first segment. And then there is a talk about climate change and how the changing climate is playing an important role in terms of how Ladakh is seen today. And since you asked me about Mars, I'll talk about the third segment, which is basically the future. So preparing for Mars exploration. And Ladakh is important in several ways. It's not just a cold, dry desert environment. There are hot springs there. Coming back to the hot springs that I spoke about, how terrestrial hot springs have played an important role in terms of understanding how life might have started. There are also these very salty lakes, Pangong So, being one of the lakes made popular by Three Idiots, and you have these different scenic lakes that a lot of people visit. But on Mars, you actually have evidence of these seas and ponds and lakes that would have existed billions of years ago. But today we find just the seabeds or the lake beds, and we find a lot of salt crusts on Mars. So what we do is we study salt crusts here on Earth that have existed at these high altitudes, exposed to high ultraviolet radiation, because you're so high up, in elevation, you're exposed to more amount of sunlight coming through the atmosphere, because the atmosphere there is very, very thin, almost 50% at some altitudes as compared to 100%, at our sea level. And you don't get enough rainfall there, so it's pretty dry. So how do these microbes that are found inside the salty shorelines in Ladakh, how do they evolve, and what kind of metabolism do they have? How are they breaking down energy? So these are the kind of things you can study there. And lastly, there are these things known as permafrost in Ladakh. So permafrost is basically permanently covered ice. So because it's so cold up there, you have these deposits of ice that are covered with soil on top of it. And this is something interesting because ice is a very good preserving medium. So over a period of time, if there are any organics that are preserved in ice, and then you have this layer of soil that covers the ice, then you have something like a time capsule. You have things that will be preserved over long periods of time. So this kind of permafrost is not found in many parts of our planet. It's formed in only cold, dry regions. Like you have them in the Arctic regions of the tundra, in Siberia, and then you have them in Antarctica and some parts of Chile in South America, and you have them in Ladakh. And the same things we see on Mars, we find this permafrost there. And one of the missions from NASA and some of the other space agencies is to further explore these permafrost regions, because we might even find trapped organics or proof of life that might have been present on Mars inside these. So Ladakh offers all of these different kinds of very distinct environments where we can probably capture the elements of how life could have been by depending on whether you're looking at the origin of life or whether you're just simply looking at how existing life could perhaps have been trapped and preserved over long periods of time. So that's how Ladakh is very, very important. And we are consciously working towards taking students and teachers to such regions to help them understand the importance of such sites and how important it is to preserve them.
Yeah, very interesting when you were speaking about the geology of the area, because we've heard about the brown water rivers that mix in with the green water rivers. And I was thinking about what you just mentioned.
That's absolutely right. How rivers transport sediments from mountains that have glaciers on top and bring them down. That's another very important feature, because we see that on Mars as well. We see how water has actually cut gullies on the slopes of mountains, and gullies are again very, very important. Those narrow channels along sloped walls of mountains and terraneous features, which actually would perhaps hold the clues of how sediments would have passed from point A, that is at a certain height, down to a lower level, and with them brought about the essential sediments or the minerals that we really are interested in.
When you talk about Mars, does the altitude or that level of altitude at Ladakh make it easier or better if you had to do viewing of the space, or you had to train a telescope into some area of space, is that also not an advantageous location to be there at right on the top in the clear day, or night rather?
Yeah, sure. So there is, in fact, an observatory in Ladakh called the Hanli Observatory, which makes perfect use of the high altitude and the low amount of atmospheric, refraction, because you're looking through a lot thinner atmosphere, and there's less dust and light pollution and everything associated with being at that specific altitude. So that's something that definitely is being done by the Indian Institute of Astrophysics, Bangalore, which remotely controls that observatory. And we also, like part of our education program, we also plan to have a much smaller observatory that we would like to establish in Ladakh. That would be a lot more accessible for participating students or other space enthusiasts who are interested in doing certain amount of astronomical measurements at that height.
I was waiting for you to say space enthusiast, because I was feeling a bit left out when all you spoke about was students, because I can't reverse time. And I was about to ask you, what about space tourism, or people who are just interested, not space tourism, but what about people who are interested in just getting there and dabbling into it?
Yeah, absolutely. The way we have set up our program is it will have two different tracks. One track will be for advanced, students who are already into their disciplines and they are interested in taking up astrobiology or planetary studies or Mars exploration, depending on what their focus is. And then there's an introductory track that is focused towards starting students. So we're looking at class 11th onwards, as well as space enthusiasts. So these are folks who are really, really passionate about space. They want a lot more out of their vacation to Ladakh than just a few pretty pictures. So we're actually partnering with a travel company called Cosmic Adventures, which in fact just got registered recently, because some of our expedition managers who are travel company people, they in fact are getting their act together, and the whole objective there is to start something like a science education or a science expedition, which is not just boring academic, scientists leading students into the field, but a lot more than that. It'll allow just regular people from all walks of life to be, because we, and especially myself and our center, we really believe that space is for everyone. It's not just meant for scientists and students. It plays a role in everybody's lives. And with that philosophy, we've ensured that whatever programs we develop, there'll always be a very strong public outreach element as well as a participatory element where regular people can participate. So absolutely, it will be open for enthusiasts to also participate.
Great. That's really nice to hear. And since we were talking about the activity on Earth and how interesting that itself is, getting up and getting into space now at the moment with all these missions, because it seems to be the Mars season, right? And there is actually a Mars season where it is the best time of the year or best time within a particular time frame to get into Mars orbit and land. Coming down to rovers on Mars and plans for landing rovers on Mars, you were speaking earlier about the Martian atmosphere, and because of the climate, the dust, the temperatures there, what were the engineering features that would be needed for a rover? Can you give us a little bit more about that particular aspect?
Yeah, so Mars, not many people know this, but Mars actually has seasons, just like Earth has seasons. And the initial rovers were actually designed to operate in only two seasons, a summer and a winter. But it so turned out that Mars also has a spring and an autumn season. By that I mean that there are certain, it's not just like on Moon where you go to Moon and if you're in the daylight you're at very high temperatures, and then when you stand in the dark you're at really, really low temperatures. So to certain level, the initial expectations were similar, that it would just be a contrast. But it turns out that for long periods of time in a year, in a Martian year, you're actually having a spring and an autumn season as well. So to ask someone what is the temperature on Mars is pretty much like asking someone on Earth that what is the temperature on Earth. It really depends on where exactly you are on the planet, at what altitude are you, and what time of the year is it. So the same things apply for Mars. But in terms of extremes, if you just had to look at the absolutes, a coldest day on Mars, which would probably be close to the poles in the winter and at night, would probably be as low as about minus 70 degrees Celsius, and which is actually not very far away from Antarctica, which anyways touches about minus 55 degrees Celsius. And the hottest you would probably would be close to the equator in summer, on a midsummer day in the afternoon, would probably be about 10 degrees Celsius, 10 to 15 degrees Celsius. So those are the temperature extremes within which you need to operate. And you're mainly concerned with the cold because electronics don't like cold temperatures. So anything that drops below minus 10 degrees, especially when you're talking about batteries or cameras or any temperature sensitive equipment, they are not going to work. So you have to design systems that can ensure that you're well insulated, you have good amount of thermal protection so that you don't freeze. So that's the temperature. Aside from that, there's a massive problem of dust on Mars, which sounds very trivial, but surprisingly it's been a massive problem for many missions, where dust seems to accumulate on top of solar panels, completely blocking out the amount of solar energy that is being received. And that leads to failure of the mission because you're not able to get all of that dust off the solar panel, and the mission basically goes to sleep. And this is actually what happened to one of the rovers, the Mars exploration rovers as well, and it kind of ended life there. So dust is a massive problem. It also tends to cause a lot of wear and tear for the moving parts of a rover. It kind of gets in the middle and then it grinds and causes problems. Dust also, you have to keep in mind is the dust that we have on Earth is actually very well rounded. The edges are very well rounded. And one of the reasons for that is the Earth's atmosphere is a lot thicker than Martian atmosphere, right? Because Martian atmosphere is just about 10% in terms of the pressure of Earth's atmosphere. So it's very thin. So the amount of dust that is flying around on Mars has not been, you can say, weathered or broken down to the same extent to what dust we find here on Earth. So it's relatively a lot more sharper, and that sharp material that's flying around can cause a lot more damage than the dust that we have here on Earth. So those are some of the different things that we as engineers worry about. And finally, there's radiation. So because Mars does not have pretty much no magnetic field protection, there's a lot of radiation that comes from space that comes down all the way to the surface. So if you're flying any instruments that are sensitive to radiation, then you have a problem. And more so when you're talking about humans going to Mars, that's again a concern where you have to build radiation protection material to ensure that the human health is not affected by all of the radiation coming from space, galactic cosmic radiation, or the radiation coming from the sun affects your rovers or your humans on the surface.
Very interesting, and we'll come to getting humans in space. But another point that you mentioned was collecting samples as part of your research or part of your study, and I think this is going to be the first time that Perseverance is going to be doing that. So one part is collecting samples, and then I guess the second part is how do you get those samples down here?
Mm-hmm. Absolutely, yeah. That's the big part of the mission, because sample return is something which is important because it allows you to do a lot more with the samples than what can be done on Mars. Because the kind of instruments that are fitted onto the rovers, they are quite limited in terms of their capabilities. So just like the lunar missions, like recently you must have read in the news that the Chinese have managed to bring back samples from the moon. And in fact, just yesterday, they had a conference where they have laid out guidelines how the international community can actually use some of this lunar regolith samples. So it's a lot easier to bring back samples from the moon because it's a lot closer. The technology needed to do that is relatively simple. But Mars is about 8 months away. It's a lot more difficult to operate a mission with the kind of communication lag that is existing, because each way, when you send a signal, it takes almost 20 minutes to reach. So many of the machines have to be automated to be able to operate on their own. And that brings in a lot of difficulties in terms of how you achieve your missions. And that's what makes things harder as well. And launching off the surface of Mars, again, is a lot more difficult because there's a lot more gravity on Mars as compared to the moon, which is 1/6 the gravity, and the gravity on Mars is 1/3 the gravity of Earth. So you need a lot more energy to be able to lift off the surface of Mars, to be able to rendezvous or dock, connect with an orbiting mission, and then bring back the samples back to Earth. So it's a very complicated affair, but it's something that is being worked on. And hopefully within the next 5 years, 5 to 6 years, we might even see samples being brought back from Mars to Earth.
Right, and we were just speaking to Piyush Kopkar, who's a student who's involved with MOXIE on this particular mission. MOXIE being the instrument that is being carried on the Perseverance to try to test the possibility of converting CO2 to oxygen. And one of the main reasons for that is, in future, if we had to have a liftoff again, that much of energy or fuel would have to be burnt. So that is quite interesting with Perseverance, that these first steps are already being taken.
Absolutely. It's been a mission that has been thought of almost for 50 years. Many people don't appreciate how well back in time that we've been talking about these missions. But for better or for worse, finally we have reached a point where we are actually going about executing these missions.
Is there any worry that people have about this particular mission?
There's always tons of worries, even though many of the systems have in fact been used by the previous Mars Science Laboratory mission. Even a repeat of that and hoping to expect similar levels of success are always daunting. So everything with regards to launch, all the way from Mars orbit insertion, and then finally landing, doing a soft land, when you're entering the Mars atmosphere, going through the whole communications breakout, and then eventually managing to have that sky crane that brings you down and then lands you. That is, I think, one of the most engineering-wise challenging things that NASA has been able to achieve. And every time they do that, there's several levels of complexities attached to it. But I think moving on from there, this mission will have it's a lot more science-heavy. It has a lot more interesting instruments attached to it, and it's also better prepared to deal with some of the problems that were faced by the Mars Science Laboratory as far as navigation is concerned, or the instrument operations and communications are concerned. So I think they'll definitely they've gained a lot, and they'll bring down some of the risks attached to it. But eventually what will happen is, breaking down the samples and collecting them, catching them, and then bringing them back. I think that's where the real complexity will really lie. And scientifically as well, the site that has been chosen, it's supposed to be a mission that, directly looks for evidence for proof of life activity. So it's not directly looking for little Martian aliens running around, but it's looking for any activity of past life. And that is always a hotly debated topic. So, you're sending a $1 billion mission, and then you want to, at the end of the day, ensure that some of those scientific questions get answered. But these are tough questions that require a lot of analysis and rigor. So I'm sure it will lead to a lot of debate and discussions that will happen. But that's the only way to do it. And that is what is being done right now.
There was some news, or there was some interesting news a few years ago when Curiosity had detected some methane in the atmosphere. Now, did that excite you as well?
It did. To a large extent, it did. But again, the analysis was, in several ways, the outcomes were inconclusive, because we still haven't been able to measure it to the extent to be able to pinpoint whether there's definitely a seasonal variation where you're seeing that the production of methane is occurring greater at some times of the year as compared to the other times of the year. But it's just making it more intriguing. It's not helping us. It's leading to more questions than leading to answers. So we that's something that needs to be further investigated.
Right. And recent reports have also spoken about, not recent, but I think reports you could say over the years have spoken about liquid water or some form of liquid below the Martian surface. Is that what you subscribe to as well?
Yeah, that has been definitely reported in some of the papers where they have actually found liquid water, and large aqueous reservoirs have been found under the surface of Mars, but then they are quite deep, several kilometers deep. So to be able to reach them is going to be a massive technical challenge. So we see a lot of salty water activity on the surface, where you must have read about how salt, when it saturates water, it tends to give it a bit of a liquidish. It is able to, so salty water is able to retain a liquid state even when it is exposed to low atmospheric pressure. So normally, when you have water in a low atmospheric condition, it will be formed in the form of ice. It is found in the form of ice. But when it is super saturated with salt, it tends to have this sluggish movement. And we recorded that. We saw that from several orbital images that were taken, where you could see that in certain seasons there was this flowing salty water on the surface, and that excited a lot of people, because liquid state of water is something that immensely can help the flow of nutrients, and that is connected with life. So again, these are things that need to be further investigated. In fact, I can tell you that 5 years back in our Ladakh expedition in 2016, we had a team that was testing out an instrument that would check how salty water behaves in low atmospheric pressure conditions. So there's an instrument that will be flying on the European ExoMars mission called Habit instrument. And we actually tested out a prototype of that instrument in Ladakh, in India itself. And some of the readings that they measured were compared with similar fieldwork that was done in Iceland as well as in Sweden, which is where the team was based. And they were able to demonstrate how that piece of technology was working. And it's now a finished package that will be flying to Mars in 2022 now.
That's interesting. Coming to humans here now. So a couple of questions for you. One, do you think that we are going to have, of course, it looks like the moon first, but do you think we're going to have human colonies on Mars? And two, if yes, what's the time frame?
I feel we will most likely see scientific bases on the moon and then eventually on Mars. That is the way how things have been going, at least in the last 4 to 6 years. There's a renewed interest. So before the Trump administration, the Americans were not keen on landing on the surface of the moon. But the way the current astronaut program is going, they're all training to, be the first humans to return to the moon and land on the surface of the moon and have a sustained presence, which by that I think they mean having a base, or at least, being on the surface on a lunar lander for longer durations than what they did in the Apollo missions. So a lot of that work will probably happen in the next, I feel, 10 years from now. I don't subscribe to it happening in the next 4 years or 5 years, but they probably might be like one-off missions. But when you're talking about presence or a semi-presence, that might take a little longer. So we're probably looking at 2030 time frame. And then same for Mars. A lot of technologies that get tested on the lunar surface would help inform the kind of technologies we need to land on Mars as well. So working from there, we're looking at probably 2035 to 2040 timeframes, so in the next 20 years or so. But when you're talking colonies, I get a bit, apprehensive, because there is a certain, assumption that there's a need to move humans to Mars, and there's a lot of people trying to say that, but that's a massive human effort with very little, government motivation to do that. Like, no government is willing to put in money, and no person can afford even going to space right now, let alone buy a trip to Mars. So, people would want to do it, but eventually it will be a very expensive and risky affair. And we certainly don't see humans settling into areas such as the, remote isolated conditions here on Earth and trying to live there. So Mars is going to be even more challenging. And how long would one be able to sustain the fascination of living on Mars? That's the biggest question. Is it something that is short-lived? Is it something that will ensure someone to be able to survive an 8-month travel and then land on another surface away from Earth and be willing to stay there for another year or 2 years before getting the chance to come back? Are they willing to stay there forever? I mean, maybe yes on paper, but eventually would they want to be part of isolation experiments where they're expected to stay isolated from everyone for over a year? So, there's several different angles attached to it. And all of those things, I think, will get figured out, but not in the next 50 years, at least, I feel. We probably will see a lot of scientific expedition work taking place, which will allow scientists to travel to these worlds and work and then return. But as far as moving regular people to Mars and living as, communities like we do here on Earth, I think we're still mindsets and a few pieces of technologies, critical technologies away from it.
I also think that in talking about moving to Mars or us finally moving away, we subconsciously are getting away from the responsibility of what we've built or what we are living on right here. Because in your mind, if you do know that that's the future, then you kind of tend not to want to invest too much in the present, because let's just talk about the future, and the present is where we are. So I think if we invest the similar or a bit of that technology, you were mentioning living in a remote place on Mars, but you could, how much of planet Earth is inhabited? So there is a lot of places on Earth that you can live and still think you're living on Mars, and make it even better and be connected as well.
That's right. There's two sides of the story, and in some ways, I'm also conflicted. I subscribe to both of them. On one side, I feel that, there's pressing problems here on Earth that deserve our attention. If one wants to escape from their way of life, you could migrate to another part of this planet, and it might be a lot more easier for you to establish yourself as compared to signing up for a mission to Mars, which currently, even in the next 20 to 30 years, we might not be ready to be able to support human civilization. But even if we were to assume that, we have a group of people, say 1,000 people on this planet, who are completely fascinated and are totally gung-ho about going to Mars, then, there's also the other side of the coin, which is, when are we going to be ready to go to Mars? You'll never be in a complete state of utopia here on this planet, where you can say finally that, okay, now, we've made our planet the best that it could be. Now is the time to think about other planets and going. That will never happen. And if you go by history, the people who traveled to new worlds or new continents and, got there, they did not really wait for things to get better or take up any responsibilities about how their own countries or their own lands would, be before they left. So at the end of the day, I think what drives movement of people is also economics. When they see better prospects for themselves, for their lives, they tend to take that risk and, be willing to move. And then where does the money come from? So, well, in the past, you had kings or royalties who would fund people to go explore, travel, set up colonies, and find vast, wealth in those regions. And then that brought people over. Well, for Mars, there isn't any such wealth waiting for us. There is a lot of resources which need to be broken down, to be constructed and formed into, basic life support. So whether that is building houses or construction material or industrial material that you would need to survive, oxygen or water or things like that, it can definitely be done if one is forced to do it. But what will drive people to do that is the ultimate question. And so far, there isn't something so pressing that would force people to let go of life here, find ways to fund it. So it's not just the drive, but also the financial requirement to be able to find ways to financially support themselves to go all the way there, and live there. So, these are all relevant and complex questions, and there isn't, I think, in my personal opinion, one side to it. So I think that, like I said, the shortest way would probably be a scientific requirement, which would further our understanding of that particular world and help develop the technologies that would be needed for it. That seems to be the next obvious step. And once a lot of that has been figured out, and for example, the lunar surface, that might be one area where humans might want to go and spend some time and then return back. That seems a lot more closer, in the horizon as compared to Mars. But even then, we are still a couple of decades away at the very least from that.
But that brings in space mining as well, right? Because if the attraction could be some exotic material or compound that drives people to put in money to go there and get it back here, and that becomes a trade route ultimately, or a trade spot.
Mm-hmm. It does. Having said all of that, there's if you look at some of the companies, there's one that recently folded, which was not able to sustain itself long enough and seem attractive enough to investors to fund it long enough. It all boils down to who's willing to put money to develop technologies to do that. And in almost certainties, it will probably be the government who would do that, who would be willing to put money towards mining space. There would be smaller efforts by private entities to do that. But in all essence, the kind of money we're talking, which is probably going to run into tens of billions, if not more, maybe 100 billions, that's the kind of money only the governments would be willing to put on it. And governments are very conservative. They normally tend to fund missions which are technology demonstrators first, and which is what is really happening. So if you look at NASA, that is the approach it has taken, where they're focusing on supporting private entities to go to the moon and be able to extract some of these minerals and be able to bring them back or break them down and turn into useful resources. So how much would a liter of water cost on the moon? That's a famous question that was posted. So it'll all happen in steps. It's not like we have the technologies in place that would allow us to extract resources even from the moon, let alone from asteroids. There's definitely precious material that is out there, but if the cost of returning it exceeds the value of that particular material, then you don't really have a game in place. So that's one thing that we fail to realize, that our technology is still fairly nascent when it comes to developing and extracting materials that would be economically valuable for us.
In your view, how unique is Earth? And when you hear the news, or when we hear the news saying that an Earth-like planet has been discovered in the Goldilocks Zone, or we hear the Goldilocks Zone, do you think that there is, for life to exist, it has to be a replica of what we have here? Why do we have to, or why are we into the Goldilocks Zone for life to exist? Because that's how we know life? Or is there a possibility for life to exist even not in the Goldilocks Zone?
So by what we have learned, our understanding of the Goldilocks Zone has become outdated, because we have seen that the kind of temperatures and pressures we have on Earth, and when I say Earth, I mean the living atmosphere in which humans live in, we don't really see life only limiting itself to that, because we have seen life exist in beyond the temperatures and pressures that we call quote unquote Earth-like. So we have seen life in a lot more colder environments on Earth, in a lot more hotter environments, a lot more pressurized, radiation-prone environments, and that has kind of broadened the Goldilocks zone, if you may. And we are now not only looking at Earth-like planets, we're also looking at Venus-like planets. We're looking at Mars-like planets. We're also interested in finding gas planets, gas giants, because we have on in our solar system, we have Europa and Enceladus, these icy moons, which are in fact some of the most promising candidate sites in our solar system where life could perhaps even be there today. That's why we're also looking for Jupiter or Saturn-like planets outside our solar system. So, like I said, the more we discover, the more questions are arising. And an Earth-like life, an Earth-like planet is, again, something which is a high-value target, but it's not the only thing that is exciting for us. There are other kinds of worlds which are obviously a lot more often that we are coming by, and we're also recording them. The challenge obviously is, once you know what it is like, what more can you get out of it? And based on different techniques, we can actually figure out their sizes, we can figure out their atmospheric composition, we can figure out their masses, their rotation rates, what kind of seasons exist. But there reaches a point where we would not know anything more unless and until we were there or we are able to send a probe there. And that's the other limitation in terms of how fast are we able to travel through space. Because in many ways, that is driven by our current rockets. And they all have a certain speed with which we can travel. So you have to be able to reach there within, centuries even, if not less, to be able to find them to be places where you can immediately confirm whether life exists there or not. So it's exciting, but again, it's a long drawn process in terms of the technology slowly catching up with what we are observing and being able to confirm by sending a probe that can take some measurements, just like we send probes to Mars and to Venus and Jupiter. We want to send similar probes to those worlds and be able to look at them up close.
Unless they make it easier for us and we have a visitation, that could be fun.
Yeah, and that's the other thing, which is SETI, right? And then
So we just jump the whole loop, and instead of us spending our time to build the technology, we get them to come right to us, and let's see what happens after that.
Absolutely, yeah.
And then we go to the "Take Me to Your Leader" line. That's going to be fun.
Absolutely, and it'll be funny to see which country they decide to visit.
So, Siddharth, currently with all that you're working on, what about the future excites you at the moment? Is there any cutting edge thought that your mind has been wandering towards, or is there something that you see is going to be the future of either space exploration or the earth sciences here on planet Earth and what we need to do here? What is it that is exciting to you at the moment?
Personally, I would like to see a renaissance of thought. I would like to find us in a situation where we are a lot more conscious of our existence, of our world, our place in this universe. And one way to do that, and this is something that we saw back in the Apollo era, where people were finally starting to, realize that life is beyond what we are constantly going through. It's to do with understanding these different worlds and connecting with that and opening up of imagination. I think that's the kind of environment that I would really like to see happen here, and it can happen in several different ways. There's obviously a lot of missions that are coming up. I'd like to see a lot more excitement about what we can do with Mars. There's several countries now sending missions up there. Any inkling of finding, confirming whether life could have existed there or not, perhaps would start new discussions. It would lead to us having a lot more discussions in the mainstream about what would be the next step. How does that affect us? Connecting a lot of that with our own planet. We're seeing, now it's happening so fast. We're seeing these unusual amount of weather activity, which was not happening when, even a couple of decades ago. So having people realize the fact that we are affecting the environment, that also is something I feel very strongly about. And what are ways in which we can change that, in which we can, be a lot more conscious to that. And I see small changes. I see people in the younger generation finally talking about these things and being conscious about these things. So who knows what the next 20, 30 to 50 years is going to be like? How are they going to be taking the planet and doing different things with it? So those are the kind of things that keep me excited. In terms of high tech stuff, I am personally interested in finding ways in which we can send smaller compact rovers that are not very expensive and do a lot more science out of them. So the NASA rover, which costs $1 billion, and it's almost a ton in terms of its weight, and it takes forever to be built and sent up there. What would be exciting is if we can shorten the time it takes to build some of these things and reduce the amount of money that is needed to launch them, because we don't want to wait for 10 years to be able to learn something. We want to see it happen in 10 months and then be able to act upon it. So basically trying to speeden up space exploration, I think, is the need of the hour. And you do that by miniaturizing instruments, building smaller vehicles, coming up with ways in which you can have a lot of communication power systems that can work in these remote conditions. Build them to be able to fit inside these compact vehicles. So those are the kind of things that I'm personally really interested in, and find ways in which you can communicate these things to regular people and make them understand, and not just see a glimmer in their eyes and then them forgetting about it next year, but finding ways in which make people understand that this is something that is the future that you are working towards, and seeing how that kind of gets into the psyche of the students. And everyone doesn't have to become a space scientist, but they have to understand and realize the importance of us being unique in our own ways and still at the same time being connected with each other. So some kind of a subconscious understanding of our place in the universe, and also being ready to face whatever is there in front of us.
And what part do you see India playing into the future when we talk about space and space research moving ahead? Do you see a major role for India here, and are we moving towards getting a little bit more deeply involved, and are we also going to probably be in the future at the head of the table?
I see India playing a very strong role as far as missions go. And we have seen that with Chandrayaan, where we were the first country, the first mission that was able to confirm the presence of water on the moon. Alongside that, the Mars mission, which was achieved in a very efficient manner, the way it was built and launched in the timeline that no other country has been able to do that. So India should really focus on playing to its strengths, and this is something that they are doing. There's several missions that have been lined up. There's a Venus mission. There are talks about having the second Mars mission, and of course there's the human spaceflight program of ISRO as well. So I think one thing which ISRO really needs to do is integrate all of these different things and find ways in which it can play to its strengths and involve more and more research and development sector people into some of their work, so that it's not just technology focused, but it's actually research and development driven in terms of achieving some of these things. And I'm quite sure that in the next 20 years, some of the major findings that will be coming out from planetary science will be from Indian missions, simply because we have the capabilities to do fast development of space missions. We have the capability of designing and learning from what the West has already done. And it's important to learn from the previous successes and failures and build on things that are unique, so you don't just reinvent the wheel and try to achieve things to show off capability, but you do it in a smart manner that it actually leads to a contribution to what is unknown, rather than trying to be a group of people that is just focused on getting ahead. You will get ahead once the thought process is such that it is focused on just kind of unveiling what is not known. So the curiosity should really be driving ISRO and the work that needs to happen, and in many ways I'm seeing that happen. So I'm actually quite encouraged by the way ISRO has been working, at least in the last half a decade or so. And in several capacities we are involved in certain roadmap building activities for ISRO as well. So the fact that they are reaching out to academic institutions and involving us into some of these discussions is actually very welcoming.
Yeah, that's very interesting. And I think we have a lot to look forward to with all these missions coming up. So, Siddharth, what would your message be to people listening to you now? And what would you like to tell them? There are going to be a lot of starry-eyed kids, probably some of them in school, college, university, deciding on careers, deciding on what path to choose. They are looking up to you, and hopefully this conversation itself, for some of them, has helped some of them make up their minds. What would you want to tell them?
I would tell them to follow whatever they currently are fascinated by, rather than waiting for a certain fascination to appear inside them about a particular field. And if you feel naturally drawn towards space, find the closest school or college that you're able to get yourself into, and just get into it. And don't worry too much about how well ranked or well positioned that particular school is, because if you're listening to my podcast, you probably understand English, and you have access to technology to do this. So consider yourself one of the very few lucky people to be able to do that. And it is important for you to continuously fuel this curiosity that you have, whether you're in school or in undergraduate, to keep thinking more and more about what you would like to do. But be action driven, keep acting upon things. And once you do that, whether you succeed or fail, you'll keep moving. And that is the most important thing. To remain static and not do anything about it is the most dangerous thing. So don't be afraid to get into a project, to sign up for a class, or take up a certain study. Even if you don't like it, you might want to drop it a year later, but that's fine. This is the time for you to figure these things out. But just make sure you have enough time for yourself for doing other things. And as long as you're passionate about space, just keep following that. And if you're interested to know more about astrobiology and Mars, we have a center of excellence that does that kind of work. And we have a very exciting project in Ladakh that I spoke about. So definitely make it a point, if you're interested to learn and experience what all of these things that I spoke about are, we'd be very happy to host you in Ladakh and talk about these things in person. So we are living in difficult times with the pandemic, but at the same time, if you look at the history of our human civilization, you're living in the best time possible. You have access to some of the best technologies, and you can do so much with it. So I'd encourage you to just keep following your passion.
And I'm sure already a lot of people would have been inspired halfway into the podcast with you. But I like what you just said. I've heard that for the first time when you spoke about following what you actually want to do, and do not think so much about the placement of the particular university, college, or the standing. So that is very deep, because ultimately, if you have the courage and you have the talent and you have the perseverance, no pun intended with that word perseverance, you will find your destination, or your destination will find you, right?
Absolutely.
So that's what happened to you.
Yeah, you need the spirit, opportunity, curiosity, and perseverance to make it to Mars.
Yeah. You need all of that. So anyway, Siddharth, it's been an absolute pleasure talking to you. I thought that we had a great conversation. There was so much we covered, and just sitting back to think about it, we did go all around Earth. We went into Earth and then back into space, and Goldilocks Zone, Mars, and the moon. You've been so patient with everything you've said, and I think you mentioned at the beginning in your introduction that you were very interested in science communication, and I think you have a natural flair for it. We've really enjoyed our time with you, Siddharth, and thank you so much for taking time. I just hope that you've enjoyed your time with us as well in some way.
Absolutely. I also did not look at the clock, because this is the only thing I talk about. So thanks for hearing out me ranting about it. But no, it's been great. I really like the way everything was covered, and like I said, I feel responsible towards all this information that I come across to pass it on. So whenever you feel that there's anything that you'd like to ask, more than welcome to reach out to me, or any other student for that matter. I try to reach out to as many students as possible. So don't be afraid to reach out or ask any stupid question that comes across.
Thank you again. And before you go, Siddharth, if people want to find you, how do they find you? If you want them to find you, or do you have some kind of a email or place that they can look for you?
Sure. So there's two ways you can find me. I am on Instagram and Twitter. My full name, that is Siddharth Pandey, SIDDHARTH and our center website is also live, so you could subscribe to that. It's www.acoeaqua.com, and we're also on Twitter, and we tweet fairly often. So those are two ways in which you could connect to me, and you can also find my contact information on the website as well, in case you want to reach out and write me an email.
Great. We'll definitely follow you, Siddharth. Indian Genes is very active on Twitter as well. We've got some very active following there, and you can, if you ever drop in there, we'll send you a note and follow you. You'll see all the action that's happening there.
Likewise, definitely. We'll follow you back, and I look forward to us trying to communicate science as much as possible in India.
इस हब हॉपर ओरिजिनल को सुनने के लिए आपका शुक्रिया। अगर आप भी अपना पॉडकास्ट लॉन्च करना चाहते हैं, तो हब हॉपर स्टूडियो वेबसाइट पे रजिस्टर करें और 1 मिनट के अंदर अंदर अपना खुद का पॉडकास्ट लॉन्च करें। यही नहीं, स्टूडियो देता है आपको पूरी आजादी कहीं भी कभी भी अपना पॉडकास्ट लॉन्च करने की, सिर्फ 3 आसान स्टेप्स में। तो साथ में अपना पॉडकास्ट शुरू करने के लिए तैयार? जस्ट हॉप ऑन हब हॉपर, सिंपली कंटेंट।